So hello you beautiful people. It's time again for chemical reaction engineering. Today is lecture 4 and we want to start with a semi-batch reactor. So first let's start with a review on the ideal chemical reactors that you should already know. This is the batch reactor. This is the easiest thing. You just fill up a reactor, then the reaction starts, and when you think it's good, then you just stop the reaction. Then we have the plug flow reactor, we have the continuous stirred tank reactor, CSTR, and we have a tank in series. The repetition, so I would normally do on the blackboard, so here I do it with my smart pen, and yes, so it's a mixture of proper slides and my bad handwriting, but I hope this is fine for you. And then we will come to something new, the semi-batch reactor. And here again you need the things you already learned. We will use the Euler Scheme for the simulation of it. And yes, and then as an outlook for the next lectures, we will also have a look at reactions with changing volume. So today the volume is changing because we are feeding one of the educts to the reactor, but you can also have a reaction where the amounts of mole is doubled or something like this, and then you also have a changing volume. And the next reactor type we will have a look at is the PFR with the recycle. So another modification. Okay, then let's start with the batch reactor. So batch reactor is just something like this. You have here your reactor. In the beginning you put in your educts. And then your governing equation would be something like dc1 over dt is equal minus r. And here component 1 should be, component 1 is an educt. That's why we write the minus sign here. And yeah, basically you will then just have something like, if you put the time here and the concentration here, then you have here your start concentration, and then you have something that looks like this. So for example, this could be something like a first order reaction. A is reacting to A2 and A1 is reacting to A2 and so on. So this is kind of a batch reactor. What you have to bear in mind, that your total time is equal to reaction time plus your time for cleaning or preparation time. So for example, if you look at a steel plant where you have an electric arc furnace, so this is something like this. This is a big vessel, and you just add in scrap, and then it takes like 40 minutes to melt down the scrap and to have liquid iron. But the overall cycle is 1 hour. So for a typical electric arc furnace, you have an operation time of 40 minutes, but it takes you 20 minutes to prepare the next heat and so on, so that your overall time cycle is 1 hour. So basically it's 2/3 operating and 1/3 not operating. So if you design something like this, then you always have to bear in mind that that your preparation time is also time consuming. Okay, this is batch reactor, and this is what you typically learn in Chemische Verfahrenstechnik 1. There are all the reactions that we have that will take place in the batch reactor. We then go to the Chemische Verfahrenstechnik 2. Then you will also get to know the plug flow reactor. So your plug flow reactor is just a long pipe, and your main assumption is that you have like a plug flow in it. So let's call it here. Holy moly, plug flow. And yeah, what is your governing equation for a plug flow reactor? So let's put it here. I put it here. This should be our PFR. The governing equation would just look the same as for the batch reactor. The one thing is that we have here the tau instead of the t. So I hope you remember. I hope you remember that if the plug flow reactor has a volume and a volume flow through this reactor is V dot, then you can just calculate the hydrodynamic mean time. Tau is V over V dot. So this is an important quantity. This is also true for the continuously stirred tank reactor. Okay, and if you do some mathematics with it, then you can just say, okay, my d tau is minus r dc, and then you can say, okay, tau is equal integral minus 1 over r dc. Okay, and then we have our integration boundaries are C10 and C1 end. Okay, and what is so nice about this equation? I hope you remember this. If you draw a plot, something like this, here you put your concentration, and on the y-axis you put 1 over r. You can get a graphic interpretation of this integral here. Okay, how does it behave if you have like a first order reaction? If we, for example, we assume something again like A1 reacts to A2, very easy first order reaction, then you have a high reaction rate when your concentration is high. So let's just say R is K times C1. If your C1 is high, then your reaction rate is high. If C1 is low, then your reaction rate is low also. And here now we have 1 over R. So if C1 is high, then 1 over R is a low value. If you have a low value of C1, then this is low, and 1 over R is then a high value. So this means that you should have something like this. Oh, didn't make it here. Okay. And what does it mean now? Now we have the integral. So let's assume this should be C10, the high concentration at your inlet of the reactor. And here this could be C1 end. And okay, what does it mean? Now we have to do the integral from C10, 1 over r dc. And this is this area here. So you can say, okay, this is my tau. You can just go to this graph, and then you can, just by identifying the area, you can see what is your what is your reactor size. So if you know your tau, then you can easily calculate your volume here from the above equation. Okay, maybe one comment about the minus here. What does it mean? So we start here with a high concentration, and then we go to the low concentration, and for this, to give it a positive value, we need the minus sign here in front of the integral, and that's why we end up with a positive value for the residence time. Okay, this was a repetition for the plug flow reactor. Then we have the continuous stir tank reactor. Should be something like this. Here you have your mixer and you have your inlet here, your outlet there. You say, okay, I have a constant volume flow going in and going out. And we also have here our inlet concentration and our outlet concentration. So if you remember the equations that we had, we said that this should be in steady state. So our left hand side is 0, and then we can say, okay, how can our concentration be influenced? You can say, okay, I have the incoming flow times the inlet concentration. I have the outgoing flow with the outgoing concentration, and then I have to take care of the reaction that takes place inside the reactor. This is minus R times the volume. And then if you play around with it a little bit, then you have something like C10 minus C1 minus R times tau. So you just divide it by V dot, and then you have your tau at the end of your equation. And here again, now we can modify this equation to get the tau, and then you have something like 1 over R C10 minus C1. Okay, let's have a look again at our diagram. Here we have C1, and here we have 1 over R. Should be a curve like this. And then you have here your C1, here you have C10. Okay. And what does it mean? So we have here the first term. I will change the color. Here you have this expression, and this is the length here. This is your difference C10 minus C1. And your other term is this is 1 over R, and the reaction rate inside your reactor, this has to be calculated with your outlet concentration. So it's this value here. So you can say, okay, this side here, this side is 1 over R. This means that our tau for the continuously stirred tank reactor is just a rectangle. So you can say, okay, this rectangle here, this is the tau for the continuous stirred tank reactor. Yes, and what else can we do? The third option, or the fourth option, is to put some tanks in series. Let me get back to red. So here you always have the same volume flow, V dot. Here you have C10, and here you have the outlet concentration, C1, of your first tank reactor, and this you send to your second tank reactor, and here you have C1, 2. So this means concentration of component 1 from the second reactor. And then again you put it to a third one, then you have here something like C1, 3, and so on. So normally they all should be the same size. So volume 1 is equal to volume 2, volume 3, and so on. And here again you can continue this for quite a while. And then, so basically every tank here in this cascade behaves like a perfect CSTR. So this means you can just say, okay, tau 1 is something like C10 minus C11 over R, tau 2 something like C11 minus C12 over R. Let's put it here like 1 for the first reactor, 2 for the second reactor, tau 3 is equal to C12 minus C13 over R3, and so on. And if you look again in our very mighty graph, here you have C1, 1 over R. Again, it should be something like this. Here you have your inlet concentration, C10. Then your first tank reactor might be something like this. Let's get blue. So this should be T1, tau 1 should be this one. Okay, if we say they all should be the same size, then we need the same area of these tank reactors. Then our second might be something like this. This is tau 2. And maybe green. Then should be something like this. This should be tau 3. Oh, my y-axis is gone. Okay. And hope you remember how it looked like. Okay. And yes. Okay. And if you now do a comparison of this 3 tank reactors with 3 reactors with the volume flow, then you can say, okay, PFR, CSTR, and tank in series. Holy moly. C1, 1 over R. Then you can say, okay, here my reaction volume or my residence time is this. If you then go for the CSTR, this, here you can see, okay, my reaction volume or residence time, something like this. And if you go for tank in series, C1 and 1 over R. Then it could look like this, okay? So if you look at this for isothermal conditions for T constant, you could say that PFR, your residence time, is smaller than tau series, and the biggest volume that you need is for the CSTR, and the same holds for the volume. PFR is smaller than volume series, and this is smaller CSTR. But remember, this is only true for constant temperature. So if you have isothermal operation, then the best choice you can do is the plug flow reactor. If it's not possible, then best use tank in series, and the worst thing you can do is use just one big continuous stir tank reactor. But this is for, I think you can say, for this is valid for your reaction rate if this is proportional to your concentration. So if you remember, for example, the autocatalytic reaction, here you have a different behavior. Here your reaction rate is not proportional to your concentration, but you have something weird going on, and there it can be very good to use a CSTR. So it always depends on your boundary conditions. Okay, this should be the repetition of chemische Verfahrenstechnik. And now let's have a look at the semi-batch reactor. So if you compare this, the batch reactor would just be something like closed system, and here your concentration is going down. And in a semi-batch reactor, this means you part of your educts you put you add at the beginning, but then one educt, for example, you could put you can add to the reactor over time. So basically it's only that you have an inflow, no outlet. You have a change in volume, because if you always feed something in, then your volume inside the reactor, your liquid volume, has to change. And what you might get is a more uniform concentration of one educt. So normally your educts go down very fast, but here, since you are adding one educt constantly over the time, you could have something more like a uniform. So it's not a straight line, we will calculate this, but you will have something more like this, and then when you end your adding of your fluid, your educt, then it will go down like this maybe. Okay, and why should you do this? The idea is that for complex reactions, the selectivity can be influenced. Let's have a look at an example. Yes, the example reaction could be an esterification. The esterification would be your acid plus an alcohol would react to a monoester and water. And for the case here, we need a dicarbon acid. Okay, I try to sketch it. The esterification we have the dicarbon acid. So, oops, I need my pen. So you have OH, C, R1, C. So this is something like a dicarbon acid, and this should react with an alcohol. So I put it here, OH, C, and here a Res2. And this reacts. This is your alcohol. And this reacts. So here you split up water, and then you have the ester of your acid and your alcohol. So this side doesn't change. OH, C, O, R1, C, O, whoops. Where was I? And then O, CR2. Okay, this is and plus water, and this should be your monoester. Okay, so this is the first reaction, but since here you have you still have one acid group left, your monoester can react again with alcohol and then produce a diester and water again. So this would then be, okay, let's start with the monoester. And just write it briefly. Monoester plus your OH, CR2. This reacts, and then you have the same reaction at the other side of your monoester, and then it becomes, now I turn it around, let's see, R2, oops, O, plus. Okay, and this would be the diester. Hope you remember this from chemical lecture or chemistry lectures, but you don't want to write it down in a very complex way. So we just write here, okay, the short version would be AC plus AL is M plus W, and M plus AL is D plus W. And yes, what we want to have is this monoester. So we want to have this reaction here. That's why we put a thumb up here. And we have the unwanted consecutive reaction. So your monoester can react with the alcohol, and then diester is formed, and we don't want to have this product. So I put a thumb down here. The reaction rate for both should be bimolecular reaction with first order to each component, and then you can write this down. Okay, and now is the question, what can we do to increase the reaction rate, to increase this reaction rate here compared to R2? Because we want to have the monoester, we want this reaction to go up and this reaction to go down. So what can we do? Okay, let's think about it. Okay, we want this up and this down, and so we want to play around with the concentrations. What can we do here? If we say, okay, let's put CAC, let's put it down, then our concentration, or then our reaction rate here, because CAC is rather low, we would have a high concentration of alcohol, and this means that this reaction here, this reaction here is then rather slow, but all the monoester that is produced by the reaction is then speeding up our reaction rate too, because here you have the high concentration of your alcohol. You have, even if it's produced rather slowly, but you have your concentration of Cm. So this means this would be faster than this one. So this is nothing that we want. We want it just the other way around. Okay. Change the color. If we say, okay, our concentration of the acid should be high and the concentration of the alcohol should be low. What does this mean? Okay, our acid, so this one, then R1 is high because we have a high concentration of our acid and a low concentration of our alcohol, but since the alcohol is also in the reaction number 2, it cancels out. So if it's low there, it's also low there. And at the beginning, we don't have, we nearly have, or we hardly have any monoester. So this reaction then is quite low. And this is quite high. And this means it should be kind of a good concept to try to have a high concentration of our acid and a low concentration of our alcohol. And this means, or not C, but acid charge at the beginning and our alcohol continuously feed to the reactor. And this means this could be a good application for our semi-batch reactor, because you put in a high amount of acid in the beginning and your alcohol you add over time. So as you can see here, you would have rather a low concentration over a long time and not something with a high start and then going down. Okay, but how can you do this? How can you calculate such a semi-batch reactor? What is new to it? The reaction volume is changing with time due to the continuous inflow of one or more educt. So this means we will use a mole balance instead of a concentration balance, and this means we have to modify our Euler scheme. I think you already learned how to use the Euler scheme for the autocatalytic reaction, and now we have to slightly adapt it. The procedure is always the same. If you know your values at Tn, then you can use all this information and with it calculate the next time step, Tn plus 1. And since I'm doing it in MATLAB, I want to start with T1, and this should be our T0. So what could be a numerical concept? Okay, first we need to know what is our reaction volume. For example, you can, if you know the total concentration, then you can just say, okay, I need all my mole amounts of all the components at time step Tn, then I multiply it with the total concentration, or in our case I will give you an example where you know the total density. So if you know the total densities, then you must know all your mass from your components, and your mass from all your components can be calculated just by the amount of moles times the molecular weight. And then you have your total mass, and with a total mass and total density you can calculate your reaction volume. Okay, if you have this, then you can calculate concentrations. This is just you divide your amount of moles for each component by the volume, then you have your concentrations. If you know the concentrations, then you can go for the reaction rates. And here we have two reaction rates, one for the wanted reaction, this is the production of the monoester, and here this is the second reaction rate, this is needed for the production of the diester. Okay, then you have to calculate your change in amount of the component, and basically this is the kind of brain work. Here you have to think a little bit. So for example, for your monoester, here you have to take into account that it is produced by the first reaction, but it is consumed by the second reaction. Then you have to multiply it by your volume and your delta T. Then your acid. For example, your acid is consumed by the first reaction, and if there's an inflow of the acid, then you have to take this also into account. So if this is your component that is added to the reactor, then you have to put it here and then multiply it with delta T. Okay, then again the diester, you have to think what is your relation for the diester. It should be quite straightforward. But maybe, yes, I will just write it down. Maybe you can stop the video for a few seconds and think about what is the delta N for the alcohol, for Tn. So if you look again here, whoops, you can see that your alcohol is consumed in both reactions and could also be fed to the reactor. This means you should write something like minus R1 at time Tn minus R2 Tn, and this times your volume at time Tn. And then there could be an inflow, then it should be dot N alcohol, and then you have to multiply it with delta T. So I think this is the most complex equation that we need for the Euler scheme. Okay, and then it's just calculate the new amounts of your component for the next time step. So it's just the old amount plus the change in your component. This is the new amount, and then repeat for the next iteration step. This means with your new mole amounts, you go here, you calculate your new volume, then you calculate your new concentrations and so on, new reaction rate, and I think you know how it works. Okay, then for an example, I somehow copied it from a book from Professor Müller-Erlwein. It's the second edition. I think it starts in the second edition, it starts at page 189. So it's not my idea, but it's the idea of Professor Müller-Erlwein. And I created a worksheet for this. Here you have all the information that you knew already, here are the two reactions. I have given you the reaction rates with the rate constants. So for R1, it's twice as high as for R2. And then, okay, let's say we will feed the alcohol for 5 hours to the reactor with a mole flow of 4 kilomoles per hour, and the total reaction time is 6 hours. And then I have here some other values. We have the total density that should be constant, 920 kilograms per cubic meter. Here you have your 6 components. We also use a solvent that is inert and doesn't change during the reaction. Here you have the mole weight of your 6 components. Here you have your starting amounts. We just start with a solvent and 20 kilomoles of your acid, and the alcohol is charged to it with a mole flow of 4 kilomoles per hour, just for 5 hours. But the total reaction time should be 6 hours. So during your reaction, you have to make sure that the inflow stops and you have 1 hour left with only the reaction in batch mode. Okay, but to see the effect of this, I said in total we want to have 3 setups. So the other setup would be that we change it. We put in the alcohol, so we put in at the beginning with 20 kilomoles, and we have a mole flow of our acid with 4 kilomole per hour, and again it's 5 hours of feeding to the reactor and 1 hour of batch reaction afterwards. And setup 3 would be that you have no mole flow to the reactor, but it's just a typical classical batch reactor, so you just have to put in your amounts of your components in the beginning, and then it's just a simple batch reaction. And with these 3 setups, we can compare and see how we can get the best or the highest amount of monoester, so our wanted product. Okay, and what you should do, if you go to the email room, they will find the worksheet. It's a PDF file, there you can read everything in detail. So there you find the worksheet. It's logically it's called worksheets, and here you have something in German it's called Aufgabe, and what I want you to do is to create the concentration profiles. So maybe you will get something that looks like, I don't know, you have something here and there and something like this. And this should be setup 1, and then second, and also a third diagram. And what I want you is to put the 3 concentration profile diagrams. You put it into one PDF, and then please upload it in this worksheet to this Aufgabe, and so that I can see how your concentration profiles look like. The deadline for this should be 1st of April, so it's rather, so you have the deadline is midnight of 1st of April, so by end of next Wednesday you should upload your files. Okay, basically that's it. Good luck with the Euler Scheme and the Semi-Batch Reactor, and then I'm looking forward to getting your concentration profiles. Take care and goodbye.